Hello. So today we're going to talk about probability, and we're going to start with sample spaces, probability models, basic probability rules, talking about some vocab, and then calculating some probabilities as well. Honestly, most of what you're going to see in this video is review. You've seen it before. We're just going to kind of formalize it, and some notations might be new, but most of the actual calculational type probability questions that we're going to see today, you have been able to calculate these for a long time. So let's jump in. So first of all, sample spaces. A sample space is a list of all possible outcomes, and there's a couple different methods that we can use to list or count a sample space. And so I would just tell you, just use whatever is easier. In different situations, different problems, the different methods might be easier or harder. So it kind of depends on what you're comfortable with and, what's going to make your life easy in that situation. So if I'm flipping a coin, the sample space, all possible outcomes, I'd probably just list out heads and tails. And there's two possible outcomes. So there's two elements in that sample space. Flipping two coins, what could I get? Again, I could get like a heads heads, a tails tails, or a heads tails, or a tails heads. I'd probably, again, just list out all possible outcomes. But I could use the multiplication principle. Remember, the multiplication principle says, well, how many things are you doing? I'm flipping two coins. So I can think about coin one and then coin two. How many possible outcomes are there on coin one? Two possible outcomes. And then on coin two, there's also two possible outcomes. So 2 times 2 is 4. So that's the multiplication principle. Flipping 3 coins, I can make an organized list and list everything out. I'll just kind of start you off. If I was making an organized list, I'd start with heads, heads, heads. And then I'd think about keeping that first heads as a heads and say, well, what else could happen? I could get tails, heads, tails, heads. I could get heads, heads, tails, or I could get heads, tails, tails, right? There's nothing else, again, keeping that first coin as a heads. There's no other combinations with those second two coins that I could come up with. So now let me change that first coin to a tails. And if I keep that first coin as a tails, what could happen on the next two? It could be heads, heads. It could be tails, heads. It could be heads, tails. Or it could be tails, tails. So those are all the possible outcomes. Again, using the multiplication principle, I'm flipping 3 coins. Each of those blanks represents the 3 coins that I'm flipping. How many outcomes are there on each? On the first coin, I could get either a heads or tails. On the second, I could get a heads or tails. And on the third, I could get a heads or tails. So the multiplication principle tells me that I can just multiply 2 times 2 times 2. And that tells me that there's 8 possible outcomes. All right, flipping 4 coins. So basically, flipping 4 coins, if you think about it, I could take all of these possible outcomes and just throw a heads in front of them. Or I could take all those possible outcomes and throw a tails in front of them. So there's going to be twice as many using the multiplication principle. First coin, second coin, third, and fourth gives me 16 possible outcomes. So we talked about making an organized list. We talked about the multiplication principle. I'm just going to quickly show you a tree diagram so you have seen one. But when I make a tree diagram, they can either go horizontal or vertically, up to you. But I'm going to think about, well, what could I get on coin 1? What could I get on coin 2, coin 3, and then coin 4? And I hope I have enough room here because these can kind of get tight. But on coin 1, I could either get a heads or a tails. Now, if I get a heads on coin 1, on coin 2, I could either get a heads or a tail. And if I get a tail on coin 1, I could get a heads or a tail on coin 2, right? Let's talk about coin 3. From here, I could get a heads or a tail. From here, I could get a heads or a tail. From here, I could get a heads or a tail. And from here, I could get a heads or a tail, and this is going to be kind of small. But now coin 4, from each of these, again, I could get a heads or a tail. Heads, tail. Okay. So now if I look kind of like at the end of this path here, whatever you're going to call it, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, heads or tails there. That tells me that there's 16 total possible outcomes, because each possible outcome represents like going down the path, like a unique path. So like, for example, one possible outcome, if I start here at coin 1, I could get a head, 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 right? Another possible outcome, if I just start at the tail, I could go like tail, head, head. So all of these kind of unique paths down my tree diagram give me each of my 16 possible outcomes. So there you go, you have a tree diagram. All right, flipping a coin and then rolling a die. So when I flip a coin, I could get a heads or a tail. And then when I roll a die, I could get a 1 through 6, right? So I'm talking about like the sample space as listing the combination of these two things. So for me, I probably would make an organized list. So I could get like a heads and a 1 on the die, a heads on the coin and a 2 on the die, a heads on the coin and a 3 on the die, etc. Or I could get a tails on the coin and a 1, 2, 3, 4, 5, or 6. So there's 12 possible outcomes. And again, using the multiplication principle, I could say, well, what am I doing? I'm flipping a coin. I'm rolling a die. How many possible outcomes on the coin? Heads or tails? How about the die? 6 possible outcomes. 2 times 6 gives you that 12. If I were to make a tree diagram, and I'm not going to make the whole thing, but I would start with like 2 columns. So I'm flipping the coin, and then I'm rolling the die. On the coin, I could get a heads or a tail. And then on the die, I could get a 1, 2, 3, 4, 5, or 6, 1, 2, 3, 4, 5, or 6, right? And that'll give me my 12 like unique paths on the tree diagram. All right, so why do we care about sample spaces? You're gonna need to be able to count the sample space pretty quickly in order to calculate probabilities. So let's talk about a probability model. And remember, a probability model has 2 parts to it. It's all possible outcomes and each of their individual outcomes probability. So an event is any collection of outcomes from some chance process. It's a subset of S. And that capital italicized S, that stands for the sample set. So an event could be just rolling a die and seeing what number you get. It could be rolling a die and getting a 5. So you could be as specific as you want. Let event A, and a lot of times we call events by like a capital letter. So let event A represent getting a sum of 5 when 2 fair dice are rolled. So if I roll 2 fair dice, how could I get a sum of a 5 when I add them together? On the first die, I could get like a 1, on the second a 4, or I could get a 2 and a 3 and a 2, or a 4 and a 1. So there's 4 possible outcomes, and there's 36 total outcomes when I roll 2 die and add them together. So because each of these outcomes, 1, 2, 3, 4, those are each of the outcomes, are equally likely, the probability of A is 4 over 36. And you can reduce that if you want to. You can give these as decimals, you can give them as fractions or as percents. So this notation might be new. Basically, like we said, you're defining a variable, but this variable is now an event in a probability model. All right, so finding probabilities. This is a formula, again, you're probably familiar with. The probability of event A is the number of outcomes in event A. In other words, the number of ways, with the previous problem, the number of ways I can roll 2 die and add them up to get a sum of a, what did we say now? I forget. A sum of a 5. And it's divided by the total number of possible outcomes in the sample space. Well, when I roll 2 die and add them together, I have 36 total possible outcomes. So we already talked about how can I come up with that denominator of that fraction. I need to come up with the total number of elements in my sample space. So these are the ways we talked about: organized list, tree diagram, multiplication principle, right? All right, let's go through some probability model examples. So remember, 2 parts to a probability model: listing out each possible element of the sample space and then finding the corresponding probability. So a lot of times probability models can be written in different ways. A lot of times you're going to see them in the form of a table. So I'm going to just show you these in the form of a table. So for each of the following events, create a probability model. And we're going to do that, we're going to list the sample space and then calculate the probability. So if event X is rolling a die, when I roll a die, Okay, I'm going to make a little table. When I roll a die, what are all my possible outcomes for X? So I'm going to start my table like this. My possible outcomes in X. I could get a 1, a 2, a 3, a 4, a 5, or a 6 when I roll a die. That's the first half. That's the sample space I just listed. And now I need to calculate the probability of each possible outcome. So on the table, I'm going to list X. Those are the outcomes when I roll the die. And then now I'm going to calculate the probability of each X. The probability of rolling a die and getting a 1 is 1 out of 6. Getting a 2, 1 out of 6. And each of these are all the same, right? So we're going to starting off with a pretty easy one, right? Okay, so that table is a probability model. All right, let's look at event Y, rolling 2 die and adding the results. So you can see over here, I have this little picture that we've looked at previously. So if I'm rolling 2 die and adding up all the results, these are all the possible outcomes that I could get. And so the smallest sum, so I'm going to start with Y, and I'm going to list out all the sample space. The smallest sum is a 2, and I can go all the way up through a 12, right? Okay, now I need the probability of each of those Y's. Now here's the thing. Each of these sums is not equally likely. Each of these 36 possible outcomes is equally likely, but some of them sum to the same number, right? So now I need to go through and count how many of them sum to 2. I know there's 36 total, right? Well, these are the only 2 that sum to 2. So the probability of getting a sum of 2 is 1 out of 36. A sum of a 3. So that would be like this one and this one, right? So that's 2 out of 36. And you can reduce these fractions just for the sake of time. I'm not going to. The sum of a 4. Here, here, and here. Those are your sums of a 4, right? So 3 out of 36. Now I want the sum of a 5. So these give you a 5, 5, 5, 5, right? So that's 4 out of 36. Now I want the sum of a 6. And you can probably kind of see the pattern that's happening here. All of these give you a 6. So there's, 1, 2, 3, 4, 5 that I highlighted in green. Oh, sorry. I wrote 5 out of 6. I meant to write 5 out of 36. So 5 of these combinations out of 36 give me a sum of a 6. So a 7, here's a 7, 7, 7, 7, 7, 7, right? So 6 out of 36. And then my sum of an 8 would be 5 out of 36. And you can probably fill in the rest of this table. You have probably done this before, or you've at least calculated probabilities like this before. You didn't necessarily call it a probability model. So again, like I said in the beginning, we're doing the same thing you've been doing before. You've done this before. We're just giving it a name and kind of formalizing things. So number 3, event Z, flipping a coin and rolling a die. So Z, all the possible outcomes. If I flip a coin and roll a die, I could get, we talked about this one before, I could get a heads and a 1, heads and a 2, heads and a 3, heads and a 4, heads and a 5, heads and a 6, or I could get a tail. Right? So those are all the possible outcomes. And then I want the probability of each outcome. Well, each of these outcomes is equally likely, right? There's 12 possible outcomes. So the probability of each is 1 out of 12. So I would just fill in a 1 out of 12. And just for the sake of time, I'm just going to draw an arrow. So all of these probabilities would be 1 out of 12. All right. And then finally, the height of AP statistics students. So my event isn't always going to be like rolling a die, flipping a coin, something like that. So in order to come up with this probability model, I would come up with a table and I would say to all of my students, well, how tall are you? How tall are you? How tall are you? How tall are you? And let's just say I have, 25 students. I would then say, okay, and actually in this question, I asked for the height of an AP statistics student. Well, how do we measure height? Typically we say like, I'm 5'4", I'm 6 foot. So in other words, we measure like to the nearest inch. I don't specify that here, but I could say like to the nearest inch. Are you 60 inches, 70 inches, whatever. And so I would, again, like list all the inches. Let's just pretend the shortest person is 60 inches, 61 inches, et cetera, and then count. Out of my 25 people or however many there were, how many of them are 60 inches? Well, if 2 out of the 25 people are 60 inches, then this probability would be 2 out of 25, right? Now, number 4 is a little trickier because like I said, I didn't really specify, like how am I measuring? Typically we measure height, like we said, to the nearest inch. But am I exactly, if I'm 5'4", like on my license it says I'm 5'4". When people say, how tall are you? I say, oh, I'm 5'4". Am I really 64 inches tall exactly? Like 64.00000 inches, right? Not really. So in example number 4 here, we call this a continuous variable because I can be like any height. I can be 61.325 inches, right? As opposed to these other ones that are discrete variables, there's a countable number of outcomes. When I roll a die, I can only get a 1, 2, 3, 4, 5, or 6. Okay. So there's some basic probability rules that those examples kind of lead us into. A valid probability model must obey these rules. So again, remember probability model. Sometimes people will freak out. Oh, what's a probability model? I forget. Remember, a probability model is just individual outcomes and the probability of each outcome. So those probability models have to follow these rules. We talked about this formula already. If all outcomes in the sample space are equally likely, here's how we calculate the individual probabilities. Probabilities always have to be a number between 0 and 1. Can they be equal to 0? Yeah. If something's impossible to happen, the probability of it occurring is 0. So for example, quickly, if I go back to this height of AP statistics students, if I am making like my probability model table here and I list height 60, 61, 62, let's say I get up to like 80 inches. If I don't have any student, which I probably don't, in my class who's 80 inches tall, the probability of having a student, the probability of having a student whose height is equal to 80 inches is 0. So that can happen, right? And I can also have a probability equal to 100 or to 1 or 100%, right? If all my students are 60 inches exactly, then the probability of a stat student being 60 inches is 100%. But it can't ever be more than 1 or 100%, and it can't ever be less than 0. If I add up all possible probabilities on that probability model table, they all have to add up to 1, always. No exception to that rule. And I'm not talking about like 0.99. I'm not talking about 1.0001. I'm talking about 1.0. The probability that an event does not occur is 1 minus the probability that the event does occur, right? What's the probability of getting a heads when you flip a coin? A half. What's the probability of getting not heads? Well, it's 1 minus a half, which is a half. So that brings us to what we call the complement rule. Now, all these rules, you've seen them before, or you probably like intuitively knew them, right? Like I said, we're just talking about notation, kind of like tightening everything up. The complement rule, and this notation might be new here, but it says the probability that A complement C is equal to 1 minus the probability of A. In other words, A complement C, that's that like superscript. So if your event is event A superscript C means A complement, like not A. So the probability of not A is 1 minus the probability of A. Okay. If we roll 2 fair dice, what's the probability that the sum is 6? So we already kind of looked at this, right? Here's all the possible outcomes when I roll 2 die that give me a sum of 6. So the probability that the sum is 6 is 5 out of 36. Notice this notation. You're going to be expected to write using this notation. Sorry, that was very sloppy. But you're going to be expected to write using this notation and be able to read this notation and know what it means. If we roll 2 fair dice, what's the probability that the sum is a 5 or a 6? Okay, well, we know that the probability that the sum is a 5 is 4 out of 36. There's 4 possible outcomes that give us a sum of 5. There's 5 possible outcomes that give us a sum of 6. I can just add those together and I get 9 out of 36, or in other words, 25%. Again, I teach this in my Algebra 1 class. You probably have learned this since you were in middle school or maybe even younger, right? But we're going to talk about this a little bit more. And this rule is going to be a little bit more complicated as we go. So the reason we can add these two things together, these two probabilities together, is only because these two events, and what are my two events? My two events are rolling 2 die and having them as a sum of 5 and having them as a sum of 6. These two events are what we call mutually exclusive, and to complicate things even more, we can also call them disjoint. As you can see, these two words, mutually exclusive and disjoint, mean exactly the same thing. They're interchangeable. When you read mutually exclusive, if you read disjoint in the next sentence, you should know that they mean the same exact thing, and you can use them interchangeably as well. Okay, so two events A and B are mutually exclusive or disjoint if they have no outcomes in common, and so can never occur together. In other words, if I roll 2 die just one time, can the sum be 5 and 6 at the same time? No. So think about it this way. The probability of rolling 2 die and the sum being 5 and 6 is 0. It's impossible for that to happen. If this is true, then the events are mutually exclusive or disjoint. So this addition rule, and this is what I call it when I teach Algebra 1. I call it the addition rule. When you say or, you add, right? That addition rule is really only applicable if two events are mutually exclusive or disjoint. So here's your rule, and you probably, like I said, have learned this before. If it's the probability of this or this, you find each individual probability and add them up. Okay, again, just another warning. We'll talk later about what if my events aren't disjoint? We'll talk later about what you do. But for right now, if they're disjoint and it says this or this, you add them together. Okay. So using the symbols, this is just a quick review of everything we've talked about, but think about this notation. So for every event A, the probability of the A has to be between 0 and 1. If S is the sample space, the probability of all the events in the sample space is equal to 1. Here's your formula for probabilities. Your complement rule that we just talked about, you need to know anytime you see that like superscript, that C, that's a complement. So like not A. And now we have our addition rule for mutually exclusive or disjoint events. Okay. Let's jump into some examples. So suppose you have an M&M's bag. You pour the candy in your hand and you observe the color. According to Mars, the maker of M&M's, this is the probability model for a bag from its one specific factory in Cleveland. So they're saying out of all the M&M's bags, this is the percent of blues, oranges, greens, yellows, reds, and browns that you could have. Notice this is a probability model because these are all possible colors listed and each of their individual probabilities. Explain why it is a valid probability model. Well, I kind of just did that. This is all possible colors, each of their probabilities, and it's valid because each of these individual probabilities have to be a number between 0 and 1, and they are. And when I add them up, I get exactly 1. And you can use your calculator to double check. But if you get 0.99999, it's a no. It's not a valid probability model. If you get 1.000001, again, it's not a valid probability model. You have to get exactly 1. So find the probability that you don't get a blue M&M. I know that you know how to do this on your own, but not blue. You can add up all of these things together, or our complement rule says that the probability of not blue, or let me write this notation down. If I define B to be picking a blue M&M, the probability of B complement is 1 minus the what am I writing here? Sorry. Is 1 minus the probability of getting a blue M&M, which is 1 minus 0.207, so 0.793. That's your complement rule along with the notation. And like I said, could I get this the other way by adding these up? Absolutely. What's the probability that you get an orange or a brown? Now think about it. How many M&Ms am I picking? I'm picking one M&M. So can it be brown and orange at the same time? No. Each M&M is only one color. So these two events are disjoint. So if I say what's the probability that you get an orange or a brown, you can find each individual probability and add them up. And again, I know you know that rule already, but I want you to connect that rule that you know and love to the definition of mutually exclusive or disjoint events. I can only add those together because when I pick one M&M, let's say I pick this one little M&M there, it can't be both brown and orange at the same time. Okay. So I'm going to use decks of cards as an example just to kind of demonstrate some of these rules and properties and things like that. So you should be like relatively familiar with these with a deck of cards, what's in it. You don't have to have this memorized. You're not expected to know this on the AP exam or whatever, but just for our purposes, if you kind of know what's happening, it'll make the examples seem a little bit easier. So there's 52 cards total in a deck, and there's clubs, diamonds, hearts, and spades. Half of those 52 cards are black, so like clubs or spades. Half of them are red, so like diamonds or hearts. And then you can get an ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king. And just one more thing to clarify, when we talk about like face cards, it's these, jacks, kings, or queens. Okay. So new definition. Union looks like a U, that like symbol there. So A union B, and remember capital letters like this, A and B, are like events. So the union, A union B, is the set of all outcomes in A or B or both. while the intersection, like an upside down U, so A intersect B is all of the events in both A and B. So if I think of my Venn diagram over here, the intersection is this like green section only. If this is, let's call this A and this B, right? The intersection is that green section only. The union is all of the outcomes in A or B or both. The whole thing. All the yellow, all the blue, all the green. And null is the empty set. That's probably familiar as well. Okay, let's look at an example. So assume we're picking cards out of a deck. Fill in the Venn diagram. We're going to define a couple events. Let's say event A is choosing a king. Event B is choosing a red card. Event C is choosing a black card. And this is going to be kind of small. But if I fill in the Venn diagram, choosing a red card, I'm just going to king, just to make it a little easier. B, red, and C is going to be black, right? So let's think about what could happen here. When you fill in a Venn diagram, you should always start in the middle, like the middleest middle. So if it's just a Venn diagram like this one up here, the yellow and blue and green one, the middle is just this green section. If it's one like this where we have 3 sections overlapping, the middleest middle, I'll call it, is like that section where all 3 overlap, right? So are there any cards, if I pull out one card, can it be a king, a black, and a red? And I'm going to erase this for a second, so, okay. All right, can it be a king, a black, and a red? No, so there's nothing listed in that middle section, right? Now, let's go like over to this section here. So can I get a card where, what's overlapping there? The king and the red. Can I get a card that's a king and a red? Yeah, if I have the king of diamonds and the king of hearts, right? Those cards are both kings and reds. Now let's move over here. Can I get a card that is a king and a black card? So yeah, so those are the cards that are kings and spades, and then the king and clubs. I can't draw them as well, so I'm just writing spades and clubs. All right, let's move down into this section. Do I have a card that's, when I pull it out, it's black and red at the same time? Excuse me, sorry. Impossible. I can't have a card that's black and red at the same time, right? So that little area is going to be blank. Now let me move up to the top here, like just this section here. Are there any kings that I haven't already filled in? No. So that top section is going to be empty. Sorry, I don't know what just happened. That's so messy. Okay, so that top section is blank. Now let me move into this section down here where like the B. Are there any cards that are red that I haven't already listed? So pretty much all the other red cards are here. So it would be like an ace, queen, jack, and then I'll just write like 2 through 10 to make it easy, of hearts and of diamonds. And then over here on the left, where it's just C, it would be the ace, queen, jack, 2 through 10, of spades, or of clubs. So there's my Venn diagram. Okay, so what is a complement? Now that we have that Venn diagram filled in, let's think about this. What is a complement? A is choosing a king, so A complement is not choosing a king. So it would be getting anything that's a 2, 3, 4, 5, 6, 7, 8, 9, jack, queen, or ace. Oh, you know what? There's no 10 in cards. Oh no. I listed the 10. I forgot the 10. Oops. I forgot the 10 here. Sorry, guys. Right? Yeah. Add that in there. Okay. What is A union B? So A union B, when I think about the Venn diagram, what section of the Venn diagram is A union B? It's anywhere where A and B are overlapping. So it's like this whole thing. And this Venn diagram is going to be kind of like messy. But it would be all of this, right? Anything that is a king or a red. So anything that's overlapping in the middle, or anything that is in just the red or just the king. So it would be all red cards, and that includes the kings, and then the king of spades, the king of clubs. Okay, oops, sorry, too quick. What is A intersect C? So A intersect C, think about in terms of that Venn diagram. I'm going to try and use another color. Like I said, this is going to get kind of ugly. But A intersect C is choosing a king and choosing a red card. So A intersect C, choosing a king and choosing a black card, because C is black card. So A intersect C in the Venn diagram is this, like, I'll color code it here, this like green section. So it would be just the king of spades and the king of clubs. All right, B intersects C. So let me get another color. I'll color code this blue. I'm sorry, this is getting really messy. But B intersects C would be the intersection of getting a red and getting a black card, right? In both A and B. So on my Venn diagram, it's where do B and C intersect? It's in this middle section here. And there are no cards that are both black and red. So we would say that's the null set. Notice, none of these are numbers. I'm not asking about probabilities. I could ask you the probability of B intersects C, and you would say it's 0. But if I ask you what is B intersects C, you would say null set. Okay. All right, so we already talked about this definition. Let's look at another example. You're driving your new car and you pull up to the stop sign in this lovely picture here. What could you do? List the sample space. Well, if I'm driving my car and I pull up to this intersection, I could either turn left or I could turn right. I can't go straight, right? I can turn left or turn right. So they are disjoint, those two events, because I can't turn both ways at the same time. I can either turn left or I can turn right. So again, picking cards, going back to similar example that we just talked about. If event A is choosing a king, event B is choosing an ace, and event C is choosing a red card. Are A and B disjoint? So A and B. Can I pick one card and have it be a king and an ace at the same time? So think about that. Think about your deck of cards. Can I pick one card and having it be a king and an ace at the same time? No, that can't happen. So they are disjoint. Or you could use anywhere where I have written disjoint here, I could say mutually exclusive. So yes, they are disjoint, or they are mutually exclusive. How about events B and C? So where's B and C? Here's B and C. Could I pick one card and have it be an ace and a red card? Could I have one card be an ace and a red card? Yes, I could have a card, or I do have some cards that are ace and red. The ace of hearts and the ace of diamonds are both aces and they're red. So because I have red cards that are aces, they are not disjoint or not mutually exclusive. Okay, how about A and C? So king and red. So can I pick a card, one card, that is both king and red? Yeah, there are cards that are kings and red. The King of Hearts and the King of Diamonds. So because I have cards that are both things, those events are not disjoint. When I pull out a King of Hearts, I'm saying it's a king and it's red at the same time. So A and C are true at the same time. So they're not disjoint or not mutually exclusive. Okay, so if two events are disjoint or mutually exclusive, then the probability of A intersect B is 0. In other words, the probability of A and B is 0. So let's think about this question right here. If we know that A and B, or in other words, choosing a king and choosing an ace, are disjoint, what's the probability of getting a card that's a king and an ace? That probability, can you pick out a card and have it be a king and an ace at the same time? It's impossible. So that probability is 0. That's supposed to be a 0. Okay. So let's look at going back to that example of rolling 2 die and adding them up together. So here's my sample space, and I just kind of have this on here again to make things easy. When I roll 2 die, and just so you know, if I had to do this on a test or a quiz, if I said create the sample space for rolling 2 die and adding them up, I would make a little table like this one right here. And I would say, okay, here's die 1. On die 1, I could get a 1, 2, 3, 4, 5, or 6. On die 2, I could get a 1, 2, 3, 4, 5, or 6. Add them up. If I get a 1 and a 1, I add to a 2. If I get a 2 and a 1, I add to a 3. 3 and a 1, I add to a 4, et cetera, et cetera. So that's how I would list the sample space. And then from there, we came up with the probability model, right? So the sum of the dice could be a 2 through a 12, and then here's all the corresponding probabilities. We already calculated these earlier, right? Okay. So here's our sample space. If I look at this example, here's my sample space, all possible outcomes. What's the probability of rolling a 2 plus a 3 plus a 4 plus a 5? Because that ... means add them all up all the way till 12, right? Add these together. 1 out of 36 plus 2 out of 36, 3 out of 36, 4. They all add up to 36 out of 36, or in other words, 1. And remember, that was one of our rules. That was one of our probability model rules. What's the probability of rolling a sum of a 3 or a 4? So you need to think to yourself, are these disjoint? If I roll 2 die, can they add up to a 3 and a 4 at the same time? They cannot. So I can add these two probabilities together. And so the probability of rolling a sum of a 3 or a 4 is 5 out of 36 because these are disjoint or mutually exclusive. Now, think about that rule that we just talked about. If two events are disjoint, what's the probability of one and the other? What's the probability of A and B? So in other words, what is the probability of rolling a sum of a 3 and a 4 at the same time? It's impossible. It can't happen. So that probability is 0. Okay, so now forget this example for a second. Think about rolling 1 die. Let's define event A as rolling a 5 and define event B as rolling an even number. What's A complement? So not A. Remember, A complement. This thing means A complement. So if I just say, what is A complement? I want you to list what are those possible outcomes. 1, 2, 3, 4, or 6. That would be rolling a 1, 2, 3, 4, or 6. If I say, what's the probability of A complement? That's when I want to say, 5 out of 6. Notice the difference between the two things. If I say what's A complement, it means list these all out, find the probability. That's when you calculate that probability. All right, B union B complement. B union B complement. Remember, union means like kind of like or. So rolling an even or rolling a not even. That would be, the evens would be like a 2, 4, or 6, and B complement would be the odds 1, 3, 5. So it would be all the possible outcomes 1, 2, 3, 4, 5, or 6. What's the probability of B union B complement? It's 1. All right. What is, and then number 5, what is B intersect B complement? So remember, intersection means like, what do they have in common? So rolling an even and rolling a number that's not an even, that would be the null set. You can't roll a number that's an even and not an even at the same time. And so therefore, if this thing is impossible, what's the probability of that thing happening? 0. Notice over here, these are the probabilities. These are the values between 0 and 1. These are all the possible outcomes. So that leads us to kind of these two additional rules. If I have event A union event A complement, that's going to give me my whole sample space. That's everything. On the other hand, A intersect A complement, that's nothing. The intersection of an event and its complement is nothing. All right. That is it for our basic probability rules. Thank you guys so much for watching. And I hope that that was helpful. Have a great day.